So hello everybody. So I'm just going to present some of my work that we used to do in the project Hello Green, which I'm associated with. And so this is the content of my presentation. And basically the work is based on developing recycled aluminum alloys for sustainable practice. And this is the project which we called Alu Green, and it's funded by the Green Platform Initiative of the government of Norway. So as you know that the aluminum is widely used as a material for the engineering components, but the primary aluminum is both cost and energy intensive. So one of the major thrusts nowadays is to move from primary to secondary aluminum, that is recycled aluminum. So it can cut the energy and the production cost to a great extent, but of course it has some demerits. So we're going to see what are the demerits. For example, there will be a lot of impurity elements in the recycled aluminums like iron, zinc, and copper. And if you have presence of these impurity elements, so this can change the mechanical properties. And we'll focus on these two mechanical properties, which you see in bold, corrosion resistant and fatigue. And also, if you notice that Norway has a long coastline, so whenever if we try to consider some components which is for fatigue sensitive application, it also comes at the cost of comes along with the corrosion. So for better design, it's imperative that we consider both fatigue and corrosion hand in hand. So to do that, so first of all, let me introduce what are the type of alloys that we use. Basically, we try to use the 3 simulated alloys, where we, rather than using post-consumer scraps, we systematically increase the elements the impurity elements like iron, copper, and zinc, so that it resembles that of the post-consumer scrap. And the material is available to us as in extruded condition. And so what we considered is the variant, which is GA3. This variant basically has the highest amount of the impurity elements in terms of iron, copper, and zinc. And basically, we carried out a high cycle fatigue test, as you can see here. And the specimens were extruded extracted perpendicular to the extrusion directions. And additionally, we did some pre-corrosion, like we subject the material to intergranular corrosion as per this method B in ISO for several different durations, like 1 hour, 4 hours, 12 and 24 hours. And we use 2 different conditions. One is as extruded without any surface treatment, and the second is as extruded followed by a surface treatment, that is glass bead blasted. And for fatigue testing, basically we did it for at a particular R ratio at 0.1 at a stress of 180 MP, and you can see the specimen geometry here. So we did a thorough microstructural characterization in terms of corrosion depth, micro hardness, and post-fracture fractography, surface roughness. And these are the outputs that we received, the stress life curve, failure mechanism, life prediction approaches. So before I go into the details, I want to show you some of the microstructure. This is the as extruded microstructure. As you can see that at the surface, we have a recrystallized layer, which are very big grains, and along with some small grains. And the recrystallized layer is followed by extruded region, which is which has a very fibrous microstructure consisting of elongated grains. And also we have like the particles, which are basically iron-rich intermetallics, which we have done EDS analysis and which revealed the particles as like this. And on the contrast, if you see the microstructure of the corroded materials, what you see is that is different. You can see that especially there is a significant intergranular corrosion, pits appearing especially in the surface region in the smaller grains, and also the intergranular cracks appearing from there and then basically moving towards the interior. And we have used this designation so that we can able to characterize the conditions more in a better manner for different corrosion durations. And in this slide, I just want to show some of the corrosion characterization in terms of maximum corrosion depth. If you look at the graph on the right-hand side, you see that we have done quite a detailed statistical analysis. We have taken the corrosion measurements on the front and the back side. And this is the box plot, which shows that with increase in corrosion duration, the corrosion depth, it increases. And this is the same for the as extruded as well as for the glass bead blasted condition. And we have also done some surface topography. And as you can see, if you compare the as extruded material, you can see that it is characterized by the extrusion lines, and you can see that which is reflected as like intermittent peaks and valleys. On the contrast, if you see that of the 24 hours corroded specimen, you see there are deep valleys. That's because the significant material loss by corrosion, formation of peats and intergranular cracks. You can see the 3D topography there. And on the other hand, if you consider the one which is the glass bead blasted, you see there is formation of bulged crater. So rather than valleys, there is some formation of peaks. And these are the variation of the roughness parameters. So you can see that the surface roughness increased significantly as we increase the corrosion duration, especially for the controlled condition. But surprisingly, if you compare this with that of the glass bead blasted condition, the roughness parameters decrease. Why is that? Because in case of glass bead blasted condition, because of the impact of those blasting, the surface roughness itself is quite high, and it is characterized by the peaks. And when the material is corroded again, what happens is the height of the peaks decreases. That's why this reduces the surface roughness. We also did some micro hardness characterization on the material, and you can see that the micro hardness, it shows an increasing trend followed by a decrease, which marks the transition from the recrystallized to the extruded zone. And for the glass bead blasted, the micro hardness is obviously higher compared to that of the controlled condition. The reason is that because of glass bead blasting, it induces some compressive residual stress and also warp hardening. So obviously it would increase the micro hardness. Now I'll come to the main result, that's the fatigue. And if you see the graph here, I have also superimposed the variation of the corrosion depth so that you can able to try to correlate how the fatigue life changes with corrosion duration vis-a-vis corrosion depth. So if you see that with increase in corrosion duration, there is a drastic reduction in fatigue life, especially for a smaller corrosion duration, 1 hour, and followed by which there is a sort of saturating trend. Surprisingly, the corrosion depth, it increases almost consistently with increase in corrosion duration. So even though there is an inverse correlation between fatigue life and corrosion duration or corrosion depth, there is this inverse correlation is not exactly synchronous. And why is that? That's because you know that fatigue is a very local damage. It requires a very small amount of just maybe 2 or 3 corrosion pieces or a tiny intergranular crack itself to initiate the crack. So even if there is a further increase in corrosion damage in terms of maximum corrosion depth, that is not very much influential in further accelerating the fatigue damage. In other words, the fatigue damage gets saturated. If you see the fractography results, so you can able to corroborate what I just said in the previous slide. So if you compare the controlled condition with that of the glass bead blasted, you see that the main difference is that in the control, the fracture fatigue crack initiates from the corner of the specimen at one of the recrystallized zone. But when you compare this with the glass bead blasted, the initiation zone moves slightly towards the interior. This is because of the impact of the glass bead blasting, because of the significant amount of the compressive residual stress that is developed, and as a result, the crack initiation zone, it moves slightly interior, and this is also the reason why you get a tremendous improvement in fatigue life. On the other hand, if you compare these results with that of the corroded conditions, you'll see even in for 1 hour corrosion duration, where the corrosion maximum corrosion depth may not be high, but you see there are multiple crack initiation sites. And contrary to a transgranular crack initiation, you can see the intergranular crack initiation because the intergranular crack is already formed as a result of the prior corrosion. If you compare these results with that of a 24-hour corrosion duration, how does it change? What the difference you can see is that in terms of when the corrosion duration is 24 hours, the corrosion damage is more higher, and that that is reflected in terms of widespread corrosion pits or intergranular cracks. So the only difference you can see here that compared to 1 hour here, almost the entire recrystallized zone is filled up with intergranular cracks or the corrosion pits. So not only it curtailed the crack initiation phase, but it probably also curtailed portion of the early stage crack propagation. So that's why compared to 1 hour, if you go to 24 hours, so that's because of the loss in the crack propagation phase, early stage crack propagation phase. Now we also try to delve into a bit of life product prediction using Murakami approach. And as you know that using Murakami approach, we basically consider some defects. Here there is no defects in terms of porosities or inhomogeneity or inclusions, but we consider the region, the corrosion pits and the intergranular crack as defects. And the effective area, we just normally what we did is that we make a contour, just considering those region, and in this way, and we measure the defect size. And if you look at the graphs here, you will see that with increase in the corrosion duration, of course, the defect size will increase. And when there is an increase in the defect size, the fatigue life decreases. But as I mentioned earlier, this increase in defect size and the decrease in fatigue life, it's not exactly synchronous. And this becomes also more clear if you look at the graph on the right-hand side. Here from the same defects, we measured the Kmax and we plot the Kmax with the fatigue life. And you can see that when you plot Kmax with fatigue life, there is a good inverse correlation in the as extruded condition, but in the glass bead blasted condition, not. Why not? Because the reason is that in glass bead blasted condition, in this case, the fatigue life is not entirely dependent on defects. It depends on so many other factors, because maybe the work hardening imparted by the impact of those glass beads or the compressive residual stress. So there may not be one-to-one correlation between the fatigue Kmax and the fatigue life. And in the graph in the bottom, you can see that we try to also predict the fatigue limit using the Murakami approach. And this gives the sort of life prediction approaches that based on the different durations of corrosion, and as expected with increase in corrosion duration, the fatigue limit decreases. So these are the main conclusions. So the corrosion damage in glass bead blasted is higher compared to as extruded, and the fatigue properties are obviously better in glass bead blasted to compare to as extruded because of the reasons I mentioned above: compressive residual stress, work hardening. But if you compare in the corrosion condition, the fatigue life, improvement in fatigue life compared to the in glass bead blasted compared to the corroded condition is less. That's because there's significant curtailing of the crack initiation phase as a result of the prior corrosion. And the kinetics of the corrosion damage, it influences the fatigue life at smaller corrosion durations, like 1 or 4 hours, because you see that beyond 1 or 4 hours, there is a sort of saturating trend in terms of fatigue life. And the life prediction approach per Murakami, it shows a good inverse correlation, but not so in case of glass bead blasted condition. So these are my recommendations for future life improvement. We should look for a suitable surface treatment method. For example, glass bead blasted, it can impart some sort of work hardening or compressive residual stress, but we have not got enough evidence that it can also change the microstructure significantly. So probably some treatments like laser shock peening could be a better option. And also we can try to determine a critical corrosion depth. This requires extensive testing for smaller corrosion durations between 0 and 1 hour. Why this critical corrosion depth is important? That's because it can able to tell us that what is the provision or what is the minimum amount of corrosion damage that we should consider for fatigue design, and without providing for the maximum corrosion depth, and also developing reliable life prediction methodologies. So we should use appropriate modifications to the defect-based approach so that we can go for a better life prediction. So I will end here, and if you have any questions, please let me know.